Hi friends, we are still in chapter 7, polynomials, and right now what we're looking at is section 7172. Please leave a little space, a lot of space actually, because we've got a lot of notes and I've got people to get rid of, so I'll talk to you very, very soon. Thank you. Okay, good, they're gone. So we're talking polynomials, we've got a lot of notes, let's get started. Now, it's not that we have a lot of vocabulary, as you see. Our vocabulary is this one term, it's called a monomial. It's the product of a number and one or more variables with non-negative integer exponents. For most of you, it sounded like blah, 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 blah. So I'll show you what monomials look like. Monomials generally are just single numbers or groupings of variables. So a monomial could be 3, chilling out by itself. It could be negative 4x squared. It could be y to the second power x to the third power t. So if you notice, these are called monomials because they're kind of alone. They're not being added or subtracted to anything else. This piece about non-negative integer exponents, that's something that's going to come into play a little bit later. But what they really are indicating is that you can't have a monomial cannot have a variable in the denominator. That's what a non-negative integer exponent basically means. So I cannot have x and then y to the third power x to the second power t. This is not a monomial. Oh, well, actually I could. Let me try x to the third power. Okay, this is not a monomial because if I cancel out the x's, which we'll talk about later, we'll end up with an x in the denominator, and that's considered not a monomial. Actually, that was news to me because I just thought any grouping multiplication. So that's what your textbook says. I'm going to go with it. I tried to look it up and see if anybody disagreed with that, and that seems to be the general thought. So you want integer exponents, and they have to be non-negative integer exponents. All right, so that's a monomial. And so we're going to test that definition out right here. So identify the monomial. So I'm just going to put an M next to things that are monomials. This is a monomial. It's by itself. It's chillaxing. Nothing's in the denominator. This is not a monomial because you've got two separate terms that are being added together. So addition, subtraction, addition and subtraction, if you see that within a expression, you know it's not a monomial. This is a monomial. There's no negative exponent, and we simply have a number, a variable here being raised to the second power. This is a monomial. I said I was going to use m's. This is a monomial. It is okay to divide by a regular number, like 2. But when I'm dividing by a variable, that makes it not a monomial. All right, according to the definition, like I said. So really what I'm thinking about when I think about monomials is I'm thinking about the fact that I just have one term, nothing being added to it or subtracted to it. And so now that we've got that, we've got some real deep stuff that I need you guys to stay with me on. These are called exponential laws, and they are super duper important to your success as a mathematician. Okay, they really are important. So I need you guys to be down with me. So basically, when we have an exponent, like if I had 3 to the second power is equal to 9, because we know that means 3 times 3 is 9, not 3 times 2. When I have 3 to the second power is equal to 9, I call 3 a base. I refer to 2 as my exponent or power, and 9 is the answer to that. And we'll leave that alone for now. All right, so what I have here is when I have a to the m times a to the n, I'm referring to two numbers with the same bases and perhaps different exponents. And basically, if I wanted to simplify this, I need to think about, and I'm going to get rid of this just a little bit, make it a little bit smaller. Go away. When I have something like this, I need to consider what's happening. So if I had 3 to the second power times 3 to the third power, that would be 2 3's being multiplied together from here, and then 3 3's being multiplied together from here. And altogether, I get 5 3's. So I end up with 3 to the 5th power. And what you notice is that I added the exponents. So when I have the same base, I'm going to add my exponents. So I get a to the m plus n. That's the rule, okay? When I have same base, pardon me, let's do 3 to the 4th power over 3 to the 2nd power. I'm going to have 3 4's being multiplied in the numerator and 4 3's being multiplied in the numerator and 2 3's being multiplied in the denominator. You see how confusing this is? And when I cancel those out, I'm left with 2 3's. 3 over 3, 3. If So what happens is basically I kind of canceled them out. And so I can write this as 3 over 2, 3 to the second power. And what I honestly did is I subtracted 4 minus 2 in order to get that. So the rule here is a to the m minus n is going to be the result if I'm dividing two numbers with the same base and different or same exponents, whatever. Doesn't matter. But we're just using two variables there. Does that make sense? Even if this was like 3 to the 5th power over 3 to the 2nd power, I'd have 5 3s up here. I'd have 2 3s down here. I'd cancel out and I'd be left with 3 to the 3rd. I know I'm overstating it, but I just want you to know that that's subtraction and not something else. All right, so a to the n to the m power. So what this is called is power to a power. When I'm raising a power to a power, I'm going to get this out of the way. When I'm raising a power to a power, what I end up doing is multiplying the exponents. So the answer is a to the n times m. I'm going to briefly show you why. If I had 3 to the 2nd power raised to the, let's say, 3rd power, this would be 3 to the 2nd power times 3 to the 2nd power times 3 to the 2nd power as per this 3rd power situation. But what would you tell me to do given the first rule? Add those bad boys up. So the answer would be 3 to the 6th. But what could I have done here to get that 6? Multiply. So that's why when I have power to a power, I multiply those powers. Here, this is pretty simple. What's happening here is that I'm raising a times b to the m power, which really means a to the m times b to the m. So if I had 2 times 3 and I'm raising it to the 2nd power, it would be 2 times 3 times 2 times 3, which I can obviously write as 2 to the 2nd power because I got 2 2's, and then 3 to the 2nd power. So this is the rationale behind this rule. And similarly, this next rule will be a to the m over b to the m. And that's pretty much all that I need in terms of that. So I could also say 2 over 3 to explain this rule, 2 over 3 to the 2nd power. Let me get rid of some of this other stuff. Okie dokie. Okay, so 2 over 3 to the 2nd power is equal to 2 over 3 times 2 over 3, which I can write as 2 to the 2nd power over 3 to the 2nd power, okay? So these are really just simplifying rules. I know I'm not actually coming up with the answer and saying, oh, 2 to the 2nd power is 4 and 3 to the 2nd power is 9. But right now, just for the point of illustrating these principles or these laws, I want to just show you how it relates to numbers that we have. So these two are pretty impressive and pretty somewhat complicated. So I am going to talk a lot, and this might actually be the end of the first video. I thought I was going to do it in one big chunk, but I think we need to get the rules down first. So I'm thinking I'm going to end this video whenever I'm done these last two, and then I'm going to start up again. So it's going to be a part 1, part 2. Which, well, you know, maybe I'll alternate that a little bit. All right, so a to the negative m power, what does that mean? So if I have a negative exponent, let's say I have 3 to the negative 2nd power. What does that mean? Well, first let's think about where we would get 3 to the negative 2nd power. So when I think about something like that, I think, oh, what if I had 3 to the 3rd over 3 to the 5th? From our rule over here, we're supposed to take the numerator's exponent, and subtract the denominator's exponent. And when I do that, I get Well, here, I'd get the same thing that I have here. I'd get 3 to the negative 2nd power, right? Because this would be 3 to the 3 minus 5, and that would be 3 to the negative 2nd power. Okay, so we see how we could get it, but what does it mean? And so here, I'm going to write this out as we did some of the other problems when we were thinking through. 3 to the 3rd power would be a bunch of 3's multiplied together. In fact, 3 3's. 3 to the 5th power would be 5 3's multiplied together. You guys with me? And then I do a little bit of canceling for us. It's very good. And when I cancel enough, I'm left with, so these guys cancel out. I get 1 over 1, 1 over 1, 1 over 1. 1 times 1 times 1 gives me 1. And then I'm left with 3 to the 2nd power down here. Since this is equal to this is equal to this, and this is equal to this, it makes total sense that I can say 3 to the negative 1/2 is equal to 1 over 3 to the 2nd power. Okay, so in a sense, I'm taking this and throwing it down here. I'm saying, okay, you got to go down here. And the sign changes. Some people talk about raising things to the negative power as, in a sense, flipping it around. And we'll talk about what that means in the next portion of our lesson. So a to the negative m is equal to 1 over a to the m power. All right. I hope that made sense. I want to make this a little bit smaller because it's looking a little confusing to me. Fix it. So, so that's what we have for this one. And finally, over here, let me make this smaller so I have some space. And finally, over here, this last one, and this is where our video will end, 8 to the 0 power. What does that mean? 8 to the 0 power is always going to equal 1, and I will tell you why. So you guys are comfortable with the idea if I have 3 to the 2nd power over 3 to the 2nd power. This rule over here tells me to subtract those exponents. So I'd have 3 to the 2 minus 2, which is 3 to the 0. Okay, but what does it mean? Remember, if you have the same thing over the same thing, right, you end up with 1. So anything to the 0 power is equal to 1, and that's how we rationalize or we think through that particular fact. All right, so I'm going to stop the video here. Please let me know if you have any questions, and we will catch up with this later. We'll talk about it in our next video. Thank you. Bye-bye.